There is a question that has kept the most brilliant minds on Earth awake at night for over a century. It is deceptively simple. It sounds like something a child might ask, and yet, after generations of effort, after billions of dollars in experiments, after thousands of peer-reviewed papers, after some of the greatest intellectual achievements in human history, the answer remains incomplete. The question is this: what is space-time? Not what does the word mean, not a textbook definition, not a metaphor about rubber sheets or fabric. The real question is deeper. What is the actual substance of the universe? What is the stage on which every star, every planet, every atom, every moment of your life plays out? And why, after more than 100 years of trying, can't we fully explain it? Visual cue. Slow zoom into a star field. The stars begin to subtly warp and bend. If you have ever looked up at the night sky and felt a quiet pull of curiosity, if you have ever wondered why things fall, why light travels, why time moves forward and never backward, then you have already brushed against this question without knowing it. Space-time is not an abstract concept reserved for physicists. It is the fabric of your existence. Every heartbeat, every step, every breath is shaped by it. And yet, most people have never been told what it actually is. Here is what makes this so strange. We live inside space-time. We are made of it. We move through it every second of every day. And yet, it remains one of the deepest unsolved puzzles in all of science. Not because we lack intelligence, not because we lack technology, but because the universe, at its deepest level, does not behave the way our minds expect it to. Visual cue. Split screen. Left side shows everyday objects falling, clocks ticking. Right side shows black holes, quantum particles flickering. Over the next hour, we're going to walk through this mystery together, step by step, layer by layer. We will look at what we actually know, what we definitely don't know, and the strange, beautiful, sometimes frustrating gaps in between. By the end, you will understand not just why space-time is so hard to grasp, but why the struggle to understand it is one of the most remarkable stories in human history. Let's begin. Before we can understand why space-time is so confusing, we need to clear away something that has been quietly misleading you your entire life. Your everyday experience, the world you see, touch, and move through every day, is giving you a deeply distorted picture of reality. Here is what you think you know. Space is empty. Time is constant. Gravity pulls things down. Objects have definite positions. The floor is solid. The clock on your wall ticks at the same speed everywhere in the universe. Every single one of those statements is wrong. Visual cue. Each statement appears on screen, then gets crossed out one by one. Let's start with space. You walk into a room and it feels empty, but it isn't. Even in the deepest vacuum, even in the void between galaxies, space is teeming with activity. Quantum fields fluctuate constantly. Particles pop into existence and vanish in fractions of a second. The vacuum is not quiet. It is a storm of invisible activity that our senses simply cannot detect. Now time. You feel it flowing steadily, 1 second after another. Tick, tick, tick. But time is not steady. It runs faster or slower, depending on how fast you are moving and how strong the gravitational field around you is. This is not a theory. This is a measured fact. GPS satellites orbiting Earth have to correct for time dilation every single day. Without those corrections, your phone's navigation would be off by kilometers within minutes. Visual cue. animation of GPS satellite orbiting Earth, with clock ticking at different speeds at different altitudes, and gravity. You were taught that gravity is a force that pulls objects together. But Einstein showed something completely different. Gravity is not a pull. It is the shape of space-time itself. Objects don't fall because something is pulling them down. They fall because space-time is curved around massive objects, and they are following the natural path through that curvature. The Earth is not pulling you toward it. You are sliding along a curved surface that you cannot see. This is where things start to get uncomfortable. Your brain evolved to help you survive on the surface of a planet where gravity feels constant, where time seems steady, and where space appears empty. Your senses are finely tuned for catching food, avoiding predators, and navigating a three-dimensional world at walking speed. They were not designed to detect the curvature of space-time, the stretching of time, or the quantum jitter of empty space. Visual cue. Human silhouettes surrounded by distorted grid representing space-time curvature. So when someone tells you that space-time bends, your first instinct is to imagine a flat surface sagging under weight. When someone tells you that time can slow down, your brain resists because you have never experienced it. When someone says that space itself can stretch, you picture a rubber sheet being pulled apart. All of those mental images are helpful starting points, but they are also wrong in important ways. And that gap between what you intuitively feel and what the universe actually does is one of the biggest reasons space-time remains so hard to understand. Not because the physics is impossible, but because your brain is working with the wrong set of assumptions. To understand where our understanding of space-time came from, we need to go back to the late 1800s. At that time, physics felt settled. Newton had described gravity as a force. Maxwell had described light as a wave. The universe seemed orderly, predictable, and well understood. There were a few small puzzles, but nothing that seemed threatening to the overall picture. Then someone tried to measure something that should have been simple. Visual cue. Historical illustration of the Michelson-Morley experiment. Mirrors, light beams, rotating table. In 1887, two physicists named Albert Michelson and Edward Morley designed an experiment to detect something called the luminiferous ether. Scientists believed that light waves must travel through some kind of medium, the way sound travels through air. They called this medium the ether, and they assumed it filled all of space. If the ether existed, then Earth's motion through it should create a detectable difference in the speed of light, depending on the direction you measured. The experiment was elegant. It split a beam of light into two perpendicular paths, reflected them back, and compared the results. If the ether existed, one path should be slightly longer than the other, due to Earth's motion. The result was stunning. There was no difference. None. The speed of light was identical in every direction. The ether did not exist, or if it did, it was undetectable. This was not a small problem. It was a crack in the foundation of physics. Visual cue. The Michelson-Morley apparatus with light beams showing no difference in path lengths. For years, physicists tried to explain this away. Some suggested that objects physically contracted in the direction of motion. Others proposed that clocks slowed down when moving through the ether. These were desperate patches, not explanations. Then, in 1905, a young patent clerk in Bern, Switzerland, published a paper that changed everything. Albert Einstein was 26 years old. He had no university position. He had no laboratory. He had a desk, a brain, and a willingness to follow logic wherever it led. His starting point was deceptively simple. He asked, what if the speed of light is the same for everyone? Not just approximately the same, exactly the same. No matter how fast you are moving, no matter what direction you are traveling, light always moves at the same speed. This sounds harmless, but the consequences are staggering. Visual cue, thought experiment, person on a train throwing a ball, then shining a light. The ball's speed adds to the train's speed, but light speed doesn't change. If the speed of light is constant, then something else must change. If you are moving very fast relative to someone else, your clocks will tick more slowly from their perspective. Your rulers will contract in the direction of motion. Time and space are not fixed. They adjust themselves to keep the speed of light constant. This was special relativity, and it meant that space and time were not separate things. They were two aspects of a single entity. A physicist named Hermann Minkowski gave it a name: spacetime. Einstein himself was not initially impressed. He reportedly said that since the mathematicians had gotten hold of relativity, he himself no longer understood it. But the math was clear. Space and time were woven together, and the speed of light was the thread that held them in place. Visual cue, 4D spacetime diagram with light cones, showing how different observers slice spacetime differently. One of the most famous consequences of special relativity is the equation E equals mc. Energy equals mass times the speed of light squared. This means that mass and energy are interchangeable. A small amount of mass contains an enormous amount of energy. This equation would later explain how the sun shines, how nuclear reactions work, and how the universe converts matter into radiation and back again. But Einstein was not finished. Special relativity only dealt with objects moving at constant speeds. It did not include gravity. And gravity was the bigger puzzle. For the next 10 years, Einstein worked on something far more ambitious. He wanted to include gravity in his picture of spacetime, and the way he did it was one of the most beautiful intellectual achievements in human history. His starting point was a thought experiment. Imagine you are standing in an elevator with no windows. You feel your feet pressing against the floor. Is it because the elevator is sitting on Earth's surface, pulled down by gravity? Or is it because the elevator is in deep space, accelerating upward at 9.8 meters per second squared? Visual cue. Two elevators side by side, one on Earth, one accelerating in space. A person inside cannot tell the difference. You cannot tell. There is no experiment you can perform inside the elevator to distinguish between gravity and acceleration. Einstein called this the equivalence principle, and it led him to a radical conclusion. If gravity and acceleration are indistinguishable, then maybe gravity is not a force at all. Maybe it is something else entirely. Here is where the idea of curved spacetime enters the picture. Imagine rolling a ball across a flat table. It travels in a straight line. Now imagine placing a heavy bowling ball in the center of the table. The surface deforms. The ball no longer travels straight. It curves toward the bowling ball, not because the bowling ball is pulling it, but because the surface itself is curved. Visual cue. Classic rubber sheet analogy. Bowling ball creates a dip. Smaller ball rolls along the curved surface. This is the analogy everyone uses, and it is helpful up to a point, but it is also misleading in a crucial way. The rubber sheet works because there is real gravity pulling the bowling ball down. The analogy uses gravity to explain gravity, that is circular. The real picture is harder to visualize. Spacetime does not curve into something else. It curves within itself. There is no larger space that spacetime sits inside. Spacetime is the container for everything. When it curves in a way that has no direction you can point to. Think of it this way. If you are walking across a dark room and the floor tilts, you feel yourself drifting. You might assume you are walking crookedly, but it is the floor that has changed, not your steps. In the same way, objects moving through curved spacetime follow paths that appear curved to us, but they are actually traveling the straightest possible route through a warped geometry. Visual cue. Animation of a planet orbiting a star. The planet follows a straight line through curved spacetime, which looks like an ellipse from the outside. Einstein spent years developing the mathematics to describe this. The equations he eventually published in 1915 are called the field equations of general relativity. They say something profound in a compact form. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. This is not just a new description of gravity. It is a completely different way of thinking about the universe. Gravity is not a force. It is geometry. The Earth orbits the Sun not because the Sun is pulling it, but because the Sun's mass curves space-time around it, and the Earth follows the natural path through that curvature. When Einstein first calculated the exact amount of bending that starlight should experience as it passes near the Sun, he got a number. It was twice the value that Newton's theory predicted. This was a testable prediction. And in 1919, a British astronomer named Arthur Eddington traveled to the island of Principe, off the west coast of Africa, to photograph stars during a total solar eclipse. Visual cue. Historical photograph of the 1919 eclipse expedition. Stars near the Sun appear shifted. The stars near the edge of the Sun appeared to be in slightly different positions than usual. Their light had been bent by the curved spacetime around the Sun. The measurements matched Einstein's prediction, not Newton's. Einstein's. The next day, newspapers around the world announced the result. Einstein became the most famous scientist on Earth overnight, and the universe had a new geometry. One of the most common misconceptions about general relativity is that it is just a theory, something abstract, something that only matters in textbooks or thought experiments. But general relativity makes predictions that can be tested, and every single test has confirmed it. Let me walk you through some of the most important experiments. Visual cue. Timeline of experiments, each appearing one by one with dates. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, conducted an experiment in a 22.5-meter tower. They shot gamma rays from the bottom to the top and measured their frequency. According to general relativity, light climbing out of a gravitational field should lose energy and shift toward the red end of the spectrum. The shift was tiny, but it was there, exactly as Einstein predicted. This was the first direct measurement of gravitational time dilation. Time literally runs slower at the bottom of the tower than at the top. Not because the clock is broken, because space-time itself flows at a different rate. In 1971, physicists Joseph Hafele and Richard Keating did something even more dramatic. They put atomic clocks on commercial airplanes and flew them around the world, once eastward and once westward. When they compared the flying clocks to clocks that stayed on the ground, the differences matched the predictions of both special and general relativity. Visual cue. World map with flight paths of the two planes, showing time differences measured. The eastward clock lost 59 nanoseconds. The westward clock gained 273 nanoseconds. These are tiny amounts, But the fact that they matched the theory exactly was stunning. Time dilation is not a thought experiment. It is a measured reality. In 2004, NASA launched a satellite called Gravity Probe B. It carried 4 of the most perfect gyroscopes ever built. The goal was to test 2 predictions of general relativity. The first was geodetic precession, the idea that Earth's mass curves space-time enough to tilt the spin axis of orbiting gyroscopes. The second was frame dragging, the idea that Earth's rotation actually drags space-time around with it, like a spoon stirring honey. Visual cue: animation of Earth rotating, with space-time grid lines being dragged around it. After years of analysis, the results confirmed both effects. Frame dragging is real. A spinning planet literally twists the fabric of space-time around it. This is not a metaphor. It is a measured physical effect. And then there is LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 facilities in the United States, one in Washington State and one in Louisiana, each with arms 4 kilometers long. They use laser beams to measure the distance between mirrors with incredible precision. On September 14, 2015, LIGO detected something that had been predicted a century earlier by Einstein himself: gravitational waves. Ripples in space-time caused by 2 black holes spiraling into each other and merging. Visual cue: LIGO signal, the characteristic chirp waveform. 2 black holes spiraling and merging. The signal lasted less than a second. The 2 black holes, each about 30 times the mass of our Sun, had been orbiting each other for billions of years. In their final moments, they spiraled together at nearly the speed of light, merging into a single black hole. The energy released in that collision was greater than the combined light of all the stars in the observable universe, and it traveled across 1.3 billion light-years of space-time to reach us. The strain, the amount of stretching and squeezing that LIGO measured, was 1/10,000th the width of a proton. That is like measuring the distance to the nearest star and detecting a change the width of a human hair. In 2019, the Event Horizon Telescope did something equally extraordinary. It created the first direct image of a black hole's shadow. The black hole at the center of the galaxy M87, 55 million light-years away, with a mass 6.5 billion times that of our Sun. Visual cue: the iconic orange ring of the M87 black hole image. The image matched the predictions of general relativity with remarkable accuracy. The size of the shadow, the shape of the bright ring, the asymmetry caused by the black hole's rotation, all of it lined up with Einstein's equations. These experiments are not abstract. They are not philosophical. They are measurements of the real universe, and they all say the same thing: general relativity works. It works beautifully. It works at scales ranging from a 22-meter tower to the collision of black holes billions of light-years away. But there is a catch. While general relativity was being confirmed experiment after experiment, another revolution was happening in physics, one that described a completely different side of reality. At the beginning of the 20th century, physicists discovered that the world of the very small does not follow the rules of classical physics. Atoms do not behave like tiny solar systems. Electrons do not orbit in neat circles. Light is not just a wave, and particles do not have definite positions until you look at them. Visual cue: animation of an electron cloud around a nucleus. Probability distributions, not orbits. This is quantum mechanics, and it is the most precisely tested theory in the history of science. Every prediction it makes has been confirmed to extraordinary accuracy. It underlies all of modern technology. Without quantum mechanics, there would be no computers, no lasers, no smartphones, no MRI machines, no internet. But quantum mechanics describes a world that is fundamentally different from the one general relativity describes. In the quantum world, particles do not have definite properties until they are measured. An electron does not have a specific position. It exists in a cloud of probabilities. It can be in multiple places at once, in a mathematical sense. When you measure it, the cloud collapses into a single point. But before the measurement, all possibilities coexist. Visual cue. Double-slit experiment. Particles passing through two slits create an interference pattern, but when observed, they behave like individual particles. This is not a limitation of our instruments. It is a fundamental feature of reality. The universe, at its smallest scales, is probabilistic, not deterministic, not predictable in the classical sense. Probabilistic. Particles can also become entangled. When two particles interact and become entangled, their properties remain connected no matter how far apart they move. If you measure one particle, the other instantly reflects a matching result. This connection does not weaken with distance. It does not travel through space. It simply exists. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experiments proving that entanglement is real and that it cannot be explained by any theory that assumes particles have hidden definite properties before measurement. Visual cue. Nobel Prize ceremony, entangled photons experiment diagram. This is strange, but it is real. And it creates a serious problem when you try to combine it with general relativity. Here is the core of the problem. We have two theories that describe the universe. General relativity describes the very large. Quantum mechanics describes the very small. Both work extraordinarily well in their domains, but they do not work together. General relativity says space-time is smooth, continuous, and curved. Objects follow definite paths through this curvature. The geometry is precise and deterministic. Quantum mechanics says nothing is smooth or definite. Everything fluctuates. Positions are uncertain. Energies jump. The vacuum itself seethes with activity. Visual cue. Split screen. Left shows smooth, curved space-time grid. Right shows quantum fluctuations and probability clouds. When you try to apply both theories at the same time, especially in places where space-time is extremely curved and extremely small, the equations break down. They produce infinities that cannot be removed. They give answers that make no physical sense. This happens in two places: at the center of black holes and at the beginning of the universe. In both cases, the conditions are so extreme that both theories should be essential. And in both cases, neither theory can provide a complete answer. The center of a black hole is what physicists call a singularity. General relativity says that all the mass of the collapsed star is crushed into a point of infinite density, infinite curvature, infinite something. But infinity is not a physical quantity. It is a sign that the theory has exceeded its limits. Visual cue. Animation zooming into a black hole center. Equations appearing and breaking apart. Question marks multiplying. Quantum mechanics does not allow infinities. It insists that quantities remain finite, that there are limits to how much you can compress or stretch anything. So when you ask what happens at the center of a black hole, the two theories disagree violently. A similar problem occurs at the beginning of the universe. If you run the expansion backward, you reach a point where everything was compressed into an incredibly tiny region. Relativity predicts a singularity. Quantum mechanics says that cannot be right. Neither theory can describe that first moment. This is not a minor inconvenience. It is a fundamental incompatibility. The two pillars of modern physics contradict each other in the regimes where both should apply, and space-time sits right at the center of that contradiction. Black holes are the most extreme objects in the universe, and they are the best laboratories we have for testing the limits of our understanding of space-time. A black hole forms when a massive star runs out of fuel and collapses under its own gravity. If the core is heavy enough, nothing can stop the collapse. The matter is crushed smaller and smaller until, according to general relativity, it reaches a point of infinite density, a singularity. Visual cue: star collapsing into a black hole, outer layers being blown away, core compressing. Around this singularity is the event horizon. This is the boundary beyond which nothing can escape. Not light, not information, not anything. From the outside, the event horizon looks like a surface, but it is not made of anything. It is a geometric boundary defined by the structure of space-time itself. Here is where things get truly strange. If you were falling into a black hole, you would cross the event horizon without noticing anything special. Time would feel normal. Space would feel normal. But to someone watching from far away, you would appear to slow down as you approach the horizon. Your light would stretch and dim. You would seem to freeze at the boundary, never quite crossing it. Visual cue: two perspectives of falling into a black hole. The falling person's view versus the distant observer's view. Both perspectives are correct. This is not an illusion. It is a consequence of how space-time curves near the event horizon. Time itself flows differently depending on your position in the gravitational field. But the real crisis comes at the singularity. General relativity predicts infinite density. Quantum mechanics says that is impossible. Something must give, and we do not know what. Then there is the information paradox. In the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon cause them to emit radiation. This is called Hawking radiation. Over incredibly long periods, this radiation carries away the black hole's mass. The black hole slowly evaporates. Visual cue: black hole surrounded by a faint glow of Hawking radiation, slowly shrinking over cosmic time. But here is the problem. If the black hole evaporates completely, what happens to the information about everything that fell in? Quantum mechanics says information cannot be destroyed. General relativity says the singularity destroys everything. These two statements cannot both be true. This is the information paradox, and it has been one of the most actively debated problems in physics for nearly 50 years. Some physicists believe the information is somehow encoded in the Hawking radiation. Others think it is stored on the surface of the event horizon. Others propose that the information escapes through quantum effects we do not yet understand. The resolution of this paradox may require a complete rethinking of what spacetime actually is. There is a problem in physics so large, so absurd, so fundamentally troubling that it has been called the worst prediction in the history of science. It involves empty space. According to quantum mechanics, the vacuum is not empty. It is filled with fields that constantly fluctuate. These fluctuations produce pairs of particles that appear and vanish in incredibly short timescales. They are called virtual particles, and they are not just theoretical. Their effects have been measured. Visual cue, animation of empty space, particles flickering in and out of existence, fields vibrating. The problem comes when you try to calculate how much energy these fluctuations contain. Quantum field theory predicts that every point in space should have an enormous amount of energy. When you add up all the contributions from all the fields at all the frequencies, you get a number. The number is 10 to the power of 120 times larger than what we actually observe. That is a 1 followed by 120 zeros. If you wrote it out, it would take pages. This is not a small discrepancy. It is not a rounding error. It is the largest mismatch between prediction and observation in the entire history of science. Visual cue. Visual comparison. Predicted vacuum energy. Enormous bar versus observed vacuum energy. Barely visible sliver. If the quantum prediction were correct, the vacuum energy would curve space-time so dramatically that the universe would either collapse instantly or expand so fast that nothing could form. No stars, no galaxies, no planets, no life. The fact that we exist means something is fundamentally wrong with either the quantum calculation or our understanding of how vacuum energy interacts with gravity. This is the vacuum catastrophe, and it sits at the exact intersection of quantum mechanics and general relativity. It is a direct consequence of trying to combine the two theories, and it tells us that something deep is missing from our picture of space-time. If the vacuum catastrophe were the only problem, physicists might be able to work around it, but it is not. There are two other mysteries that reveal how little we understand about the universe. In the 1970s, astronomer Vera Rubin discovered something strange. Galaxies were rotating wrong. The stars at the edges of galaxies were moving much faster than they should have been based on the visible mass. According to Newtonian gravity, those stars should have been flung off into space, but they weren't. They were held in place by something invisible. Visual cue. Galaxy rotation curve. Predicted falling versus observed flat. The simplest explanation was that there must be more mass than we could see. Something that does not emit light, does not reflect light, does not interact with electromagnetic radiation at all. Something that only reveals itself through gravity. Scientists called it dark matter. Decades later, we still do not know what dark matter is. We have built enormous detectors deep underground to try to catch dark matter particles. We have searched for them at the Large Hadron Collider. We have mapped their gravitational effects across the sky, and we have found nothing definitive. Dark matter makes up about 27% of the universe. Regular matter, everything you can see and touch, makes up about 5%. The rest is something even stranger. Visual cue. Pie chart of the universe. 5% regular matter, 27% dark matter, 68% dark energy. In 1998, two teams of astronomers were studying distant supernovae to measure how the expansion of the universe was slowing down. What they found was the opposite. The expansion was not slowing down. It was speeding up. Something was pushing space-time apart. Something with negative pressure. Something that acted everywhere, uniformly, without clustering or forming structures. Scientists called it dark energy, and it makes up about 68% of the universe. We do not know what dark energy is. We can describe its effects mathematically. We can measure how fast it is pushing the universe apart, but we cannot explain its origin, its mechanism, or its nature. Together, dark matter and dark energy make up 95% of the universe. Everything we understand, every atom, every force, every particle we have ever detected, represents only 5% of what is out there. The vast majority of the universe is made of things we cannot see, cannot touch, and cannot explain. Visual cue. The observable universe fading into darkness, with 95% unknown appearing. This is not a small gap in our knowledge, it is a chasm. And it tells us that our understanding of space-time, the stage on which all of this plays out, is profoundly incomplete. Now we arrive at one of the deepest questions in all of physics. Is space-time a fundamental building block of reality? Or is it something that emerges from something deeper? This might sound like a philosophical question, but it is not. It is a physical question with physical consequences, and the answer could reshape our entire understanding of the universe. Let me explain what I mean by fundamental versus emergent. Consider temperature. You can feel it. You can measure it. It is completely real. But temperature is not fundamental. It emerges from the motion of countless atoms and molecules. A single atom does not have a temperature, but a collection of atoms does. Temperature is a collective property that arises from something more basic. Visual cue. Single atom vibrating, no temperature label. To billions of atoms vibrating, temperature label appears. Could space-time be like that? Could it be real, measurable, and observable, but not fundamental? Could it emerge from something deeper, the way temperature emerges from atomic motion? There are reasons to think it might be. The first clue comes from entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a remarkable idea called ER equal to EPR. They suggested that entangled particles might be connected by tiny wormholes, bridges in space-time. If this is true, then the connections between quantum states might actually be creating the geometry of space-time itself. Visual cue. Two entangled particles connected by a worm-like bridge with ER equal to EPR label. Think about that for a moment. Space-time might not be the stage on which quantum mechanics plays out. Quantum mechanics might be the process that creates space-time. The geometry of the universe might be woven from entanglement. Another clue comes from the holographic principle. In the 1990s, physicists Gerard Hooft and Leonard Susskind proposed that all the information contained in a volume of space can be encoded on its boundary. This was inspired by black hole physics, where the entropy of a black hole is proportional to its surface area, not its volume. Visual cue. 3D volume of space with information lines converging onto a 2D surface. In 1997, Juan Maldacena made this concrete with the AD-CFT correspondence. He showed that a theory of gravity in a certain type of curved spacetime is exactly equivalent to a quantum theory without gravity living on the boundary of that spacetime. Two completely different descriptions, one with gravity and one without, producing identical physics. This suggests that space-time might be a kind of projection, a three-dimensional reality emerging from a two-dimensional description. Not an illusion, but an emergent structure, like the surface of water appearing smooth even though it is made of molecules. A third approach comes from Erik Verlinde, a Dutch physicist who proposed that gravity might be an entropic force. Just as temperature emerges from statistical mechanics, gravity might emerge from changes in information. When an object moves through a region of space, the information associated with that region changes, and the force we call gravity might be the universe's way of responding to that change. Visual cue. Object moving through a grid of information bits with entropic force arrows appearing. These ideas are speculative. None of them have been proven, but they all point in the same direction. Spacetime might not be the foundation of reality. It might be a layer of description resting on something deeper, something we have not yet identified. If this is true, it would explain why general relativity and quantum mechanics are incompatible. They might be describing different levels of the same reality. General relativity describes the emergent geometry. Quantum mechanics describes the underlying structure, and the two levels do not match because they are not the same thing. The holographic principle deserves its own chapter because it is one of the most mind-bending ideas in modern physics, and it might be the closest thing we have to a bridge between general relativity and quantum mechanics. The idea started with black holes. In the 1970s, Jacob Bekenstein proposed that black holes have entropy. This was controversial because entropy is a measure of disorder, and black holes seemed like the most orderly objects in the universe. But Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. Visual cue. Black hole with event horizon highlighted. Area measurement increasing as mass increases. This was strange. If you have a box full of gas, the entropy depends on the volume of the box. But for a black hole, it depends on the surface area. This suggested that all the information about what is inside the black hole might be encoded on its two-dimensional surface. Susskind and Hooft extended this idea. They propose that this is not just true for black holes. It might be true for any region of space. All the information in a volume of space might be representable on the boundary of that volume. If this is correct, then the three-dimensional world we experience might be a kind of holographic projection. The information that defines reality lives on a two-dimensional surface, and the three-dimensional world, including space-time itself, emerges from that information. Visual cue. A 3D room with objects dissolving into patterns on the walls, like a hologram being projected. Maldaceni's odd-Z CFT correspondence provided a concrete mathematical example of this. He showed that a specific theory of quantum gravity in a 5-dimensional curved space-time is exactly equivalent to a 4-dimensional quantum theory without gravity on the boundary. The two descriptions are mathematically identical. Every calculation in one theory can be translated into the other. This is the closest thing we have to a theory of quantum gravity. It does not solve all the problems. The space-time in Maldaceni's model is not exactly like our universe, but it shows that a complete theory of quantum gravity might exist, and it suggests that space-time is not fundamental. If the holographic principle is correct, then space-time is emergent. It arises from quantum information processes on a lower dimensional surface. The smooth geometry we experience is like the smooth surface of water, real at our scale, but composed of something much more fundamental at a smaller scale. For decades, physicists have been trying to build a theory that unifies general relativity and quantum mechanics. Several approaches have come tantalizingly close, but none have succeeded completely. String theory is the most famous attempt. Instead of treating particles as points, string theory imagines them as tiny vibrating strings. Different vibrations produce different particles. One vibration mode behaves exactly like the graviton, the hypothetical quantum of gravity. This was the first theory to include gravity naturally without producing infinities. Visual cue. Tiny strings vibrating in different modes. each mode producing a different particle. But string theory requires extra dimensions, 10 or 11, depending on the version. We only observe 4, 3 space plus time. The extra dimensions must be curled up so small that we cannot see them. String theory also produces an enormous number of possible solutions, perhaps 10 to the power of 500. Each solution describes a different possible universe. This is called the landscape problem, and it makes the theory very difficult to test. Loop quantum gravity takes a different approach. Instead of adding extra dimensions, it tries to quantize spacetime itself. It proposes that space is made of discrete loops woven together into a network. At the smallest scales, space is not smooth. It is granular, like a fabric made of tiny threads. Visual cue. Zooming into smooth space, revealing a network of loops at the Planck scale. Loop quantum gravity naturally avoids infinities. It predicts that quantities like density and curvature have maximum values. It does not require extra dimensions, but it has struggled to reproduce the smooth spacetime of general relativity at large scales. And it has not yet been tested experimentally. Causal set theory proposes that spacetime emerges from a network of discrete events connected by causal relationships. Events that can influence each other are linked. Events that cannot are not. The geometry of spacetime emerges from the pattern of these connections. Visual cue. Network of dots connected by lines, gradually forming a smooth surface. This approach is elegant and background independent, but it is still in its early stages. It has not yet produced testable predictions that distinguish it from other theories. Asymptotic safety suggests that gravity might be renormalizable at high energies. This means that the infinities that plague quantum gravity might be tamed by a mathematical trick. If this is true, general relativity might be a complete theory after all, valid at all scales. Each of these theories captures part of the truth. None captures all of it. They are like different pieces of a puzzle that do not quite fit together. But the fact that multiple approaches exist, each with its own strengths, suggests that the answer might involve elements from several of them. Before we finish, I want to pause and acknowledge something important. It is easy to focus on what we do not know. The mysteries are dramatic. The gaps are large. The unanswered questions are profound. But we should not lose sight of what we have achieved. Visual cue. Montage of human scientific achievements. Telescopes, particle accelerators, space missions, equations on blackboards. General relativity is one of the most beautiful and successful theories in the history of science. It describes the motion of planets, the bending of light, the expansion of the universe, the collision of black holes, and the flow of time itself. Every prediction it has made has been confirmed. GPS satellites rely on it. Gravitational wave observatories depend on it. Our understanding of the cosmos is built on it. Quantum mechanics is even more successful in its domain. It describes the behavior of atoms, molecules, particles, and fields with extraordinary precision. It underlies all of modern technology. Without it, there would be no computers, no lasers, no smartphones, no internet, no modern medicine. We have detected gravitational waves from colliding black holes. We have photographed the shadow of a black hole 55 million light-years away. We have measured the expansion of the universe and discovered that it is accelerating. We have mapped the cosmic microwave background radiation and used it to determine the age, composition, and geometry of the universe. Visual cue. timeline of discoveries, from Newton to Einstein to LIGO to EHT. We have built the standard model of particle physics, which describes every known particle and every known force except gravity. It predicted the existence of the Higgs boson decades before it was discovered. It has been tested to extraordinary precision. These are not small achievements. They are among the greatest intellectual accomplishments in human history. The fact that space-time remains partially mysterious does not diminish what we have learned. It simply means there is more to discover. And that is not a failure. That is an invitation. So where do we go from here? The next breakthrough might come from new experiments. Gravitational wave observatories are becoming more sensitive. New telescopes are mapping the universe with unprecedented detail. Particle accelerators are probing smaller scales. Each new observation has the potential to reveal something unexpected. The breakthrough might come from new mathematics. Many of the greatest advances in physics came from mathematical insights that did not initially seem connected to reality. Non-Euclidean geometry seemed abstract until it described curved spacetime. Complex numbers seemed imaginary until they explained quantum wave functions. There may be mathematical structures waiting to be discovered that will make the behavior of space-time look obvious in hindsight. Visual cue. Abstract mathematical structures transforming into physical phenomena. The breakthrough might come from a completely new perspective. Perhaps space-time is not the right starting point. Perhaps the universe is better described in terms of information, relationships, or processes rather than geometry. Perhaps the answer requires thinking in ways that do not rely on spatial intuition at all. Or perhaps the breakthrough has already happened, and we have not yet recognized its significance. The ER equal to EPR conjecture, the holographic principle, emergent gravity. These ideas might contain the seeds of the next revolution. They might be waiting for someone to connect them in a way that no one has thought of yet. Visual cue. Puzzle pieces floating in space, slowly beginning to fit together. What I can tell you is this: the mystery of space-time is not a sign that physics is failing. It is a sign that physics is alive. It is growing. It is reaching for something deeper. Every generation of scientists adds a piece. Every experiment narrows the possibilities. Every theory, even the ones that fail, teaches us something about the shape of the truth. We are not at the end of the story. We are somewhere in the middle, and the chapters that come next might be the most remarkable of all. The universe has been holding this secret for 13.8 billion years. It is in no hurry, and neither are we. Visual cue. Slow pull back from Earth, through the solar system, through the galaxy, through the observable universe, into darkness. A single line of text appears. The mystery continues.